Okay, so in this class, we'll discuss these questions on your tuition note, okay, starting from 26 up to how much we can complete. Let's see. Okay, go to page 118, where there is question 26. So let us see here, question number 26. Let me read it for us. State Newton's third law of motion. We have done already with the first. This chapter is called force and laws of motion. So the first two laws of motion we have discussed, right? So today we're going to discuss Newton's third law. So you can write it down on your tuition copy and open your tuition note and follow with it, okay? Textbook also, you can keep it. Newton's third law of motion. So let us read here. I'll read the answer for us. Page 118, tuition note. Newton's third law of motion states that when a body exerts a force on another body, means there's two bodies involved here, the second body will instantaneously exert an equal and opposite force on the first. Okay, so here what does that mean is simply this. Suppose I have here two objects, just to make us understand. Let us say these two are moving objects and they collide. Okay, so you know that before they collide, this pen on my right hand has a force and a pen on my left hand has a force. They may be same or different, doesn't matter. But when they collide, you see, this pen on the right hand will exert a force on this second pen. Let's say this is the second pen. At the same time they collide, not only the first pen exert a force on second pen, but the second object here, pen, also will exert a force. And this third law is saying the amount of force which the first object apply on the second object when they collide, and the amount of force the second object will exert on the first are exactly equal and also opposite in direction. You see, the first object has a force acting from left to right. Second object, this pen is from, the force is exerting from right to left. So they are opposite. When they collide, each will exert a force on each other. And the force applied by first object on the second object, and the force applied by the second object on the first object when they collide will be equal, number one. And number two, they will be opposite in direction. So that's what Newton's third law is saying. So anytime two objects collide, for example, I press this board with a force. Now you see that the board is stationary. There is no movement here. So when a force is applied on this stationary board, the board also applies an equal but opposite direction force on my hand. So when I apply a force on the board, by just simple observation, we seem as if only the hand is applying the force on the board. But Newton's third law is saying that that is not true. When you apply a force on this board, the same amount of force your hand is applying on this stationary board, that same amount of force is also applied by the board on your hand, and these two forces are not in the same direction, they are in opposite direction. Okay, so that is called Newton's third law. Now go to the next question, 27. In Newton's third law of motion, the force exerted by the first body on the second body is called action or action force. And the force exerted by the second body on the first body is called reaction or reaction force. So if you take this as the first object and this one as the second object or body, when they collide, the force exerted by this first object on the second object, that force is called action or action force. And the force applied by the second body on the first object, which is equal but opposite in direction, is called reaction or reaction force. So in every collision or every contact of a force with another object, there is always action force, which is the force exerted by first object on the second object, and the force exerted by the second object on the first object, which is equal in magnitude but opposite in direction to the first object, is called reaction force. So you tick there yes. Okay, now go to 27. 27 is repeated on your tuition note, but it's okay. Second 27. Okay, thus Newton's third law of motion, if this is so, we can redefine it also like this, that for every action means action force, there is always an equal but opposite reaction or reaction force? Yes. Once we come to know what is action and reaction, for every action there is an equal and opposite reaction or reaction force. Tick there, yes. 28. It must be remembered that the action and the reaction forces always act on two different objects and never on the same object. Tick there, yes. I'll explain this to you. What does that mean? So the force exerted by the first object on the second object when they collide here is called action force. And so that force is acting on the second object. And the force exerted by the second object on the first object is called reaction force. And that reaction force is not acting on itself but on the first object. So this is saying in Newton's third law, the action and reaction forces, they never act on the same object. They act on different object. Means action force X is the force acting on the second object, and reaction force is the exclusive force exerted by second object on the first object. So action and reaction forces, these two forces never act on the same object but on the other object, on the different object. Okay, so tick there, yes. Now let us do 29. 29 is simply saying this. What does 29 say? Okay, question number 29. Here, illustrate means prove Newton's third law with a simple example. So for this, you tie here, you'll get this on the wall, permanently tied to a hook, a spring balance. Spring balance means a balance that you find in some shops, right? To measure 1 kg aloo, that 2 kg aloo, that can measure weight, but actually it's measuring mass. Oh, sorry, measuring force. Okay, spring balance is used to measure force exerted. So this is the first spring balance, let us say. So there is a reading scale here, let us say 0, 1, 2, 3 newtons, like this. Newton, 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 let us say 4, whatever, 5. Then you hook it up. There's a hook always on a spring balance. The hook is something like this. So hook it up. Now hook it up with the other one. From the other spring balance, this hook is coming. So there's a second spring balance. You can draw along with me. Okay, so here, hook it up. Then, so this is the second spring balance. So this is the free end with a hook here. So this side you're going to pull with your finger. Same reading. So here is the scale. So 0, 1, sorry, 2, 3, 4, 5, etc. Newton, Newton, Newton. Because force, the unit is Newton, we know that. So as you pull this one with 1 Newton, the reading will be 1. If you pull a force, this balance with 2 Newton, the reading will be 2. Like that, it will show. So now, in the beginning, before you pull, this is fixed to a wall. Right. So before you pull these two in the opposite direction, the reading on this spring, both spring balances will be 0, meaning no force has yet been applied. That means now you've pull with your finger, let us say, up to 2 Newton force. You can see from the scale. So adjust your force, the strength of your hand. That means to make your force apply 2 Newton. When you do that, you observe this side. You find out that the reading is also exactly 2 Newton. That means the force exerted by this spring balance on this is 2 Newton. You make sure with your finger. That time the force exerted by spring balance, let's say this is A and B, force exerted by spring balance B on A is 2 Newton. At that time you will find out that the force exerted by spring balance A on B, reaction force, is also exactly equal to Newton, and they are in opposite direction. So this proves. Now you increase it to 3 Newton or 4 Newton, then here also will read 4 Newton. Again, validating or proving that the force exerted by B on A balance is exactly equal to force exerted by A on B balance. Keep on doing, go to 5 Newton, here also 5. So this proves that Newton's third law is true. Let us read through now. 29, let me read the answer. Okay, sorry. Here. Let two spring balances be connected together as shown in the figures I've explained here, with the fixed end of the balance B being fixed to the rigid support like a wall. So I've explained it. So it doesn't move. When a force is applied through the free end, that means with your finger apply a force on the free side, not the wall side, it is observed that both spring balances show the same reading on their scales, means the force exerted on both balances are equal, right? This means that the force exerted by balance A on B is equal to, but opposite in direction to the force exerted by B on A. Here the force which A exerts on B is called action force. A exerts on B, okay, I took it B to A, but you can also, up to you, B on A action, then A on B reaction. In your note, A on B is taken as action. Up to you, but you can take that one as action, the other one, okay? A on B is action. Force, action, is called action, and the force which balance B exerts on A will be called reaction in that case, or reaction force. Thus, for every action, there is equal and opposite reaction. We have proved by this simple illustration that Newton's third law is such a basic concept, so true in real life, right? So now go to 30, okay? Keep it simple. This chapter is not hard, but you will need some imagination because physics is such a chapter that we're studying physical quantities and things that we do not see with your eye or smell. So we need our imagination, right? So if you're willing to do that, imagine, then it's not hard, okay? But you need to listen carefully, imagine a lot, and things will be simple. 30, question number 30. Let us see what is 30 saying. Okay, let me read. Explain how second and third laws of motion works in the act of walking. So when we are walking on the road, how can you explain that act of you walking on the road by first and second law, by the second and third law? Now remember, second law says that force is directly proportional to acceleration, right? Force is directly proportional to, if you go back once to the second law, see page 114, Newton's second law of motion states that the rate of change of momentum of an object is directly proportional to the applied unbalanced force and takes place in the direction of force. So force is directly proportional to rate of change of momentum, which is here to start working. So second law, to start working from rest, answer, you must accelerate, means you must give acceleration, which requires a force. So if you know, accelerate means move, basically increase in velocity means move, right? So for an object to start moving with increasing velocity, you need a force, because nothing will move on itself. A force is needed. In accordance to the second law of motion, we know this, that for a body to start increasing in velocity, it means accelerate or moving, you need to apply a force, right? So we learned that in second law. This force is nothing but the push on the rod. So when you walk, you're pushing the rod with your feet, right? Bottom part of your feet. That is the force that you apply to accelerate your body, right? To walk with the second law. This force is your push of the rod below backwards. So you're pushing the rod backwards. Of course, the rod is not moving, but you're actually trying to, in the act of walking, you're trying to push the rod backwards in a sense, right? Now, according to the third law of motion, the rod, according to the third law of motion, when you apply a force backwards on the pushing the rod backwards to accelerate your body forward, that object, the rod, will also apply an equal and opposite force on your leg. Now your leg is pushing the rod backwards, so the rod will push your body or leg forward, because it, according to third law, the other object will act with equal but opposite direction force, right? So this force is your push of the rod below backwards. Now according to the third law of motion, the rod will exert an equal and opposite reaction force on your feet to make you move forward, because reaction is opposite to action. Action is your act of pushing the rod backwards. So reaction force, the force exerted by the rod on your leg, will be forward. So because of which the rod pushing your leg forward, reaction force, you begin to move forward. So thus we see that in the act of walking, second and third laws of motion are involved, right? So that's it. Question 31. Let me read, look there in your tuition note. Even though action and reaction forces are always equal in magnitude, these forces may not produce accelerations of equal magnitude. Why? Explain it with an example. This question is simply saying this, question number 31, okay, 31. So you see here, according to second law, F is equal to ma. So that means A will be equal to F divided by m. So we see that acceleration and m is in the denominator, means they are inversely proportional. Inversely proportional means as m increase, the mass of an object increase, the acceleration, the movement will decrease. Inversely proportional means increase on one side, increase in mass causes decrease in acceleration. And when one is on the numerator and the other side is in the denominator, that is always inversely proportional. When both are numerator, that is directly proportional. Directly proportional means increase on one side also causes increase on the other side. Increase on one side causes decrease on the other side is called inversely. Denominator means inversely. So as the mass of an object increases, acceleration decreases. We know this even in real life. For example, you push this ball with this force, you see, and it'll move very fast with this slight small force push also. Now you do the same thing like this I did, see here, and it's moving very fast. You do the same thing on a heavy car, it will not move at all. Same force. That proves that as the mass of the car is so huge, acceleration is almost zero. But here, the slight push is moving the slight ball very fast. So we see this in real life, that as the mass of an object increases, the acceleration decreases, meaning the force which pushed this ball very fast, slight push of my hand, is not going to move the heavy car because the mass is so huge. We know this. The question is saying, why is this so? The same force which pushed the ball very fast means produces a large acceleration on a small ball, doesn't even move the car with a heavy mass. We know that, but why? So the answer is this. As the mass increases, by Newton's second law equation, we see that as m increases, a will decrease. So Newton's second law explains that to us. So let us read through it once. We know that F, this is the answer, okay? So here, we know F equal to ma, so A will be equal to F by m as I wrote here. That is for the same force, acceleration is inversely proportional to mass. You know, inversely. I already explained in previous classes also, but inversely proportional is something like this. 5 girls sweep this room for 10 minutes. Let us say 5 girls sweep this room, taking 10 minutes time, number of girls. Then if you double the girls, they'll take less time now, 5 minutes. So as the number of girls increase, time taken by them to sweep a particular area will decrease. So this is inversely proportional. So we write here, number of girls is inversely proportional to the time, denominator. So inversely, like that's the denominator. So as mass increase, acceleration will decrease. As mass decrease, acceleration will increase, right? So that is for the same force, acceleration is inversely proportional to mass. Hence, the same force applied to two different masses will produce more acceleration in the lighter mass. So this force, same force that I apply, slight force, moves this light ball, very less mass, very fast. But the same force that I put on the heavy car does not even move the car. See? More acceleration on the lighter object and less acceleration on the higher mass object, even though the force is same. Okay, so let me read once more. For the same force, acceleration is inversely proportional to mass, as we see from this equation. Hence, the same force applied on two different masses will produce more acceleration on the lighter mass as compared to the higher mass. Thus, even though action and reaction forces are always equal, according to third law, in magnitude, these forces do not produce accelerations of equal magnitude. It will produce higher acceleration in the mass, in the lower mass, and produce less acceleration in the case of higher mass for the same force. Example, let us take here. This will make you understand, I think. You take a gun and you fire, you see? As you fire the gun, the bullet moves forward with a very high acceleration. Means acceleration in simple words is speed. So with a very high speed. At the same time, according to Newton's third law, the bullet moving forward will apply an equal and opposite force on the gun that you're holding. That's why when you shoot a gun, it recoils and hits your shoulder backwards. But because the mass of the gun is heavy, that force, that is reaction force acting backwards, which is equal to the force acting on the bullet, because of the heavy mass of the gun, the acceleration behind the recoil that is the force backwards on your shoulder, is always lesser. That's why when you shoot, the bullet moves with a very high acceleration forward, because the bullet is such a small mass, but the same force of the bullet that is applied on your gun hardly moves your shoulder, slightly only, because the mass is so huge. Therefore, the same force that is moving the bullet so fast is just moving your shoulder a little bit only, right? Let me read that for us now. 120. This is an example of how the same force that moves the bullet so fast, small mass, moves your gun with very less acceleration, right? When a gun is fired, a force is exerted on a bullet. This is called action, the force on the bullet to move forward. So the bullet exerts an equal and opposite reaction force on the gun. This is called reaction force, or in specific term for gun shooting is called recoil, okay? The force on your shoulder backwards. But since the gun's mass is much higher than the bullet, the acceleration on the gun is much lesser than on the bullet. As you know in experience, the bullet moves so fast, and the same force that moves the bullet so fast is moving your gun backwards so slow, very little, because the gun's mass is quite heavy, right? So this proves it. 32. As a person moves forward out of a rowing boat, he exerts an action force on the boat. At the same time, the boat exerts an equal and opposite reaction force on his feet, and the boat moves backwards. This is always experienced. This is an example of the third law of motion in operation. Yes, tick there, yes. So when you come out of the boat from the water, your leg is pushing the boat backward. That is action force. But at the same time, the boat will act on your feet with an equal and opposite reaction to push your body forward, and it itself moves backward. That is an example of Newton's third law in operation, right? So 33. This is question similar to 31. Action and reaction forces, which are always equal in magnitude according to the third law of motion, will produce equal accelerations on two objects of equal masses. Yes, when the two objects are of same masses like this, the reaction force that when they collide, the force of a first object on second object and the force of second object on the first object will produce same acceleration when both are of same mass. When this is higher mass and lower mass, the same force will produce more acceleration in the smaller mass and less acceleration in the higher mass, right? So that is it. Yes. 34. Action and reaction forces, which are always equal in magnitude according to the third law of motion, produce more acceleration in the lighter mass as compared to the higher mass according to the second law of, or according to the second law of motion. Yes, we discussed that just now, right? 31, the bullet shooting. Now, state the law of conservation of momentum. Let's see whether we can do this or not. Okay, so here, okay, we will do this next two questions, 35 and 36 in the next class, because this is important. In a separate class we'll do it. So up to 34 we have done today. Up to 34, write down. And then up to 34, so up to page number 120. Next class we will be doing two more important questions, 35 and 36. Law of conservation of momentum and derivation of the formula connected to it. And after that, numerical tests only are left, okay? 4 or 5 numerical tests are there, okay? So this concludes the class. I hope you have understood it, okay?